I'm Olga from JOYA team. I'm going to talk about, the title is a little bit different. I'm talking about the missing link, the micro-optics implementation in AR development. So I want to start actually with you people. See, in this conference there are two major groups of people. I call them, the first group is ideas people. Jessica also talked in her talk yesterday, and she called this group application experts. So I call them ideas people. Actually, these are people that develop products, applications, cover use cases. And the second group is technologies people, technologies expert. You probably recognize some of the presenting companies here from the images. And these are companies that develop technologies, new materials, manufacturing processes, and manufacture parts and optics, and micro-optics in this conference mainly. So what we do in JOYA team, we connect these two groups of people, create the link between them, and find the points for cooperation between these two groups so they can work together and develop products. So we are JOYA team, a small and young company, almost 6 years old, but we have a huge experience, mainly in AR field and XR applications. So these are part of the products, AR or XR products that we have been part of development, engineering, and design through our experience. You probably recognize the glasses with the red nose we've been showing here around to people. One of the newest AR products, Brilliant Take from Brilliant Labs. And most of the people that talk about micro-optics application in augmented reality, they refer to waveguides, diffractive holographic solutions. I'm going to talk about more fundamental conventional optics and how micro-optics can be valuable in augmented reality systems. So my first example would be like something that most of you know already familiar with, is using micro-optics in sensing applications that are also used in augmented reality, such as eye trackers, ambient light trackers, and all kinds of trackers. So in general, it looks like this. You have photodiodes. Sometimes you have color filters on top of them, and you have light falling down, whether it's ambient light or projected light falling down on the photodiodes, and you can see that a lot of light misses the active area and creates not very good solutions. So the idea is use micro lenses to kind of focus the light onto the photodiode active area, and this is idea enables to control and shape sensing numerical aperture, but the numerical aperture is actually the effective angle that is effective in this sensing application. And the idea of using microlens provides the values of improving efficiency, improving effective fill factor, and improving signal-to-noise ratio of the sensing application. So this is commonly known, already used application, and I'm going to show you how to take the same idea and twist it to a different application, which is more unique to augmented reality systems. So in augmented reality, we use micro displays to project them to the user's eyes, and some of the macro displays, they require illumination to work, such as LCDs, LCOS, DLPs, and others. So in this case, we have sources like LEDs, and their angular span is very wide, and it's not controllable. It is what it is. Most of the time, it's like Lambert channel or very wide. And if you imagine some element on top of the structure, a lot of light misses this element, like optics, and is going to waste or creating unwanted effects. So the idea is to put micro lenses on top of the sources and direct and align the light towards the optical element. As you can see, the lenses are different for different part of the illumination system. They can be used in a way to align more precisely the illumination and make it like more focused towards the optics. So this idea enables to control and shape the illumination numerical aperture. In this case, it also gives the values of improving efficiency, improving contrast, and reducing stray light. When stray light is the unwanted light that travels inside the system but not going through the optics and through the main path, and it creates effects like white glow, white screen, or some strange artifacts that people do not want in their system. So, I'm taking this idea also to different type of micro displays, which are self-emitting, like OLEDs or micro LEDs. And also, in this case, their angular span is very wide, so you have the subpixels, you have color filters, and you have light emitted to all the directions, and a lot of it misses the optics again, and it's not efficient. So here also you can put like micro lens layer on top of the display to focus the light and align it towards the optical element. And here the idea enables to control and shape the image source numerical aperture also to improve efficiency, improve contrast, and also reduce stray light, as in the previous example. So you may ask, why do we need to work this hard to put the micro lenses on all these applications? What does it give on a system level? So I'm gonna step back and talk about AR system or XR system. They have regularly three main blocks in the system. You have the micro display, you have the optics, and you have the system pupil, where is the area where the user's eyes can be located and to get the full performances of the system. So in general, it goes like this: different points of micro display go through optics and reach the system pupil, and you can see here that only the blue area is the effective system pupil, because you see there the whole field of view. And a lot of light misses this area because in other areas you will see only partial field of view and not full field of view, and that's very wasteful. And the idea that I showed before, with controlling illumination numerical aperture, we align the emission of the illumination part through the optics toward the system pupil, and only this area is illuminating. This enables to improve efficiency, improve system contrast, and reduce stray light. It could be called exit pupil aiming, because you from the beginning you aim through the system only towards the effective system pupil, which is the useful area. But I want to take this idea even more complex level. Instead of controlled illumination numerical aperture, we can have variable illumination numerical aperture, which would be even smaller and which would be aligned towards the working pupil, which is the actual pupil of the user's eyes. So in this case, we even focus the light even further towards the actual working pupil. We can use eye tracking methods to follow the user's eye gaze and position. So in this case, we gain even more from this idea of working pupil aiming and tracking. The first one would be reduced eye glow. A lot of times you see in in AR systems, like a big flashlight on the user's eyes, where the illumination goes, and it's really not nice looking, uncomfortable. Here you illuminate only on the pupil, and it's a lot more aesthetic. And this idea also solves as personal fitting apparatus to track and follow the eye gaze of the user. So you would ask, maybe, it looks very nice on presentation, how do you do this in practice? So what we do, we develop step-by-step process when we work from the idea and use case for every project, and we select the optimal technologies. We actually use this to combine also and link between the ideas people and the technologies people and find the best solution and optimal technologies that work in each application. And also this link has to be maintained through the whole project, because technologies grow and sometimes they disappear, sometimes new technologies evolve, and from R&D phase they go to more mature state and they become available, and we want to use them for our customers. And one of the things that we're here for is to learn all these technologies from a lot of people here that also show abilities and implement them into the design for our customers. So we do this by combining our doing pyramid, which is based on our experience in optics and expertise in augmented reality. I also want to mention our close collaboration with Synopsys on using and also developing the best-in-line software tools, Code5 and Light tools, and our ability to combine between imaging and non-imaging design tools. Because when I'm talking about illumination and stray light, it is a non-imaging aspect of a system. And when I'm talking about field of view and resolution, it's an imaging aspect. And our ability to combine these two fields is very, very crucial and unique. And we have more of our building blocks here, but I want to mention in particular the top yellow one, which is a smiley here. We enjoy what we do. We like it, and we do it with a smile, and we believe in creating personal and good relationship with our customers and our partners. And everything that we do is wrapped around with our state of being, our core values that guide us through everything that we do and help us work with people like yourselves. And I want to finish up with a nice sentence by Henry Ford. You can read it. I invite you to work together and create brilliant and successful products together, linking the ideas and technologies to create products. Thank you for your attention.